come to the last part of Module 8, where we're actually going to look at using the z-curve, but in an opposite direction. We are going to be finding boundary values when we are given areas or probabilities. Previously, when we looked at our z-table, and if you have your z-table, you should grab it, we're going to look first at how to find this on our table. In the previous section, in 8.4, we used the z-table to find given probabilities. In this section, we're actually going to use the z-table, but in a reverse fashion. This is helpful when we want to find boundaries of the curve that correspond to a given probability or a given area. For example, what z-value has an area of 0.0301 to its left? Well, we know if we're on the left-hand side of the curve, 3%, of course, is a very small number. It's less than 50%, very much so, less than 50%. So that can tell us already where on the curve we are. We have to be to the left of 0 on the standard golden curve. So if we go to the negative area of our z table, and we look in the body, we look until we come as close to 0.0301 as we can. In this case, we can come right to it, 0.0301. Then we can locate what z-value it corresponds with. In this case, we have negative 1.8 and then 8 in the hundredths place. This tells me that my z-value that corresponds to having 3.101% to its left is negative 1.88. Let's look at another example. Find the z-value using your table that has 0.065 or 6.5%, again, to its left. We go to the table, we see that 0.065 is a very low percentage again, so it's going to be on the negative part of our z-table. And as we look through it, we get as close as we can to it. The closest one we probably recognize, first of all, is 0.0655. But of course, this is 5/10,000ths more than the area we're actually after. It has an extra 5 there. If we look to the left of that, we can see that this also is fairly close to 0.065. It's off by negative 7, and in this case it should be 10,000ths. So one is off by 5/10,000ths, the other is off by 7/10,000ths. So obviously this one is closer. And typically, if we didn't have technology, this is what we would go with. We would say the z-value that corresponds to this area is negative 1.51. But with this example, you can see how limited our z-table really is. Because the z-values on our table only go to the hundredth spot, to the second decimal place, we are only limited to the areas of z-values that stop at the hundredth spot and don't have zeros following it. Therefore, in this section, we're going to focus mostly on technology. And in a moment, we will go back and revisit this problem using our calculators. Example 3, though, I want to look at before we do, asks us to find a z-score that has an area of 0.025 to its right. This, of course, is different. And as you know, the z-table is only limited to areas that are to its left. So, just looking at a normal curve, we're going to look at 2 ways that we can accomplish this that I think illustrate a really important point. The first method is to complement what would be the complement of this area. If we know there's 0.0250 to the right, then we can look at what would be to the left of that value. If I take 1 minus that value, we see the area to its left is 0.9750. That would be the area over on this side. Then, if we look up this in our z-table, or if we use our technology, we can calculate that the z-value is 1.96. 1.96 actually has 0.97 or 97.5% of the data to its left. So when we're given an area to the right, one of the ways that we can find the area is to take its complement. The second way to accomplish this is to use the property of symmetry with my curves. If I know I want to find 0.0250 to the right, we can use the fact that on the left-hand side of the curve, we can find that same area. In other words, this is the value we're after. But if I know that 2.5% or 0.025 is what I'm after, I can look for that here in my z-values in my table, and we can see here that 0.0250 is the area that I'm really after, and it corresponds with negative 1.96, the same value that we found earlier, except it's negative. And so because of symmetry, we can just ignore the negative and make it positive, and know that positive 1.96 will correspond to the same negative 1.96, 2.5% to its left. And positive 1.96 will have 2.5% or 0.0250 to its right. So those are two ways of doing it. And it's important to be able to get somewhat comfortable with both ways, because sometimes either comes in handy as we're trying to look this up. This is another reason why you always want to draw pictures for these problems. The students that I see that draw pictures consistently for these types of problems dealing with the normal curve end up gaining a greater understanding of what they're doing and what it is that they're after. Now let's go back to the technology question. How to find z-values, or in general, boundary values for a given area or probability. We're going to lead with an example going back to the one from a couple slides ago, where we were after the z-value with 0.065 to its left. As you recall, negative 1.51 was as close as we could get to this area, but it was a little bit more. The function on your calculator is under the same screen where you found normal CDF. It's just the choice right beneath it. It's number 3. So we go second parse, which is your distribution page, and then negative number 3, invert norm. There's 3 things you're going to have to enter. The first one is what you want to put is what the area to the left of the boundary value we're after is. This will be given to you in this type of problem. Sometimes it may not directly be given to you, but that's what you want to figure out, what the area would be to the left of the value you're after. Second, and of course you put a comma, we're going to enter what the mean is. If we're dealing with the z-value, of course the mean is always 0 on the standard normal curve and z-values. And then third, we want to enter what the standard deviation. Again, for z-values, it's always 1. So here's how it looks. Invert norm, we have 0.065 to its left, 0 for our mean, 1 for our standard deviation, and we get a more specific z-value. You can see I've rounded it up to the third decimal place, negative 1.514. It's important to remember that the first number is always the area to the left of whatever value you're after, just like it is on the z-table. Even if what you're given is an area to the right, you need to find out what the area would be to its left. So, taking another example. Here we're going to find the z-value such that the area to its left, to the left of the negative z-value, plus the area to the right of the positive z-value is 0.1, or 10%. Taking a picture of this scenario, let's see, we're actually after 2 boundary values. And if we draw this picture, we can kind of get an idea of what we're doing. Reading it again, it says find the value of z such that the area to the left of negative z, that would be this area over here, so the left-hand tail, plus the area to the right of positive z, that would be over here in the right-hand tail, has a sum total of 10%. Since the total is 0.1 or 10%, we have to divide it up if we want to know what the area is in each tail. It should divide evenly because, again, my curve is symmetric. So in each tail, we have 5%, 0.05. This is important to draw out as we want to input the correct values that you're after into your calculator. Remember, calculators can only give you correct answers as you put in correct information. So now we have two choices. Do we want to pursue this z value, or do we want to pursue this z value? It doesn't really matter which we pursue, because we know that one will just be the opposite sign of the other. If I go for the one on the left, I'm going to put 0.05, 0, 1. The area to its left is 5%. And we see we get negative 1.645. If I pursue the value on the right, I need to keep in mind that the area to its left between here and here would be 90%, but then we're adding another 5. Because we don't stop when we're putting the area to the left, it's from our value all the way back to negative infinity. And so if I'm going for the one on the right, I actually want to put invert norm 0.95%. Or not 95%, but 0.95. Another way to think of that, if that confuses you, is remember, there's 5% to the right. And so if we were to take the complement of that, we would have 95%. 95% and 5% gives me 1. And when you input that in, you should get positive 1.645. Like I said, no matter which one you decide to find, just remember that the other one will have the opposite sign. So, here's some more questions for us to quiz ourselves with. What z value has an area of 0.8888 to its left? The answer? Go ahead and see if you can find it. In fact, I'm going to put several of these up here. Go through, pause this, and then see if you can find the area. Remember to draw a picture to correspond with these so that you don't make a mistake on the signs. Now that you've calculated these and drawn your pictures, here are the answers. Z equals 1.22, Z equals 1.88, and Z equals positive and negative 1.96. The last question, before you move on, is what Z value represents a 95th percentile? A 95th percentile, the word 95th percentile, means that the percent of the data to its left is whatever the percentile is you're looking at. So for example, if I say Bobby fit into the 95th percentile of his class, that means 95% of the people had a lower GPA than he did, and 5% had a GPA higher than he did. So the 95th percentile means 95% is to its left and 5% is to its right. So if you can locate that on an old curve and figure out what z value would represent the 95th percentile. The answer is 1.645. Now let's look at some actual data values dealing with real world data. Going back to the body temperatures that we looked at in the previous section, we see that the body temperatures of adults are normally distributed with a mean of 98.6 and a standard deviation of 0.73. The question is, what temperature represents the 95th percentile? Again, what body temperature will 95% of the population be below, 5% be above? If we look at that from the picture, we can see that 95% would be below this temperature and 5% would be above. So we're on the right-hand side of 98.6. In this problem, we're actually told what the mean and the standard deviation is of our data set. So 0.95 is the area to its left, 98.6 is the mean, and 0.73 is my standard deviation. calculating this out, we see 99.8 is the body temperature of the 95th percentile. Remember that 98.6 was right here in the center, and 99.8 is higher than that. So this fits with what we should expect, and if we're to the right of 98.6, we should have a higher value than 98.6. Here are a couple more problems for you to do. Go ahead and pause it, see if you can figure out this. The answer for this problem is 110.8 and 189.2. The trick to this problem is to remember we're looking for a middle 95%. That would leave 2.5% on the left-hand tail and 2.5% on the right-hand tail. 2.5%, of course, is half of 5%. There's two boundaries, and so we need to divide up this remaining 5% by 2. So my left-hand side has 2.5% of the tail, right-hand side has 2.5% of the tail. And so as we're calculating, for example, if you want to find this value, our area to the left would be 0.025, comma, the mean of the standard of this distribution, which is 150 pounds, comma, the standard deviation of the distribution, which is 20 pounds. So invert norm 0.025, comma, 150, comma, 20 gives us this value. For the right-hand side, we're not going to put 95% as the area to the left. We're going to use 97.5 because 2.5 is to its right. That means 97.5 is to the left. Comma, 150, comma, 20, and you should get 189.2. Here, with these parameters, 110 minutes and standard deviation of 33, you're asked what the third quartile value is for cell phone units. Remember, that third quartile is another word for the 75th percentile. The third quartile has 75% to its left, and so that's what you want to put as your area to the left. The answer that you should get is 132.11 minutes. This concludes this part of Module 8.